Welcome to Advanced Linear Algebra. Today we are going to explore one of the most magical, surprising and powerful results in all of matrix theory, the Cayley-Hamilton Theorem. Whether you are studying pure mathematics, physics or engineering, understanding how a matrix interacts with its own defining polynomial will completely change the way you look at linear systems. Let us dive in and uncover how this incredible theorem works from the ground up. To begin, imagine you buy a complex industrial coffee machine, and it comes with a unique diagnostic barcode printed on the back. In linear algebra, a square matrix is exactly like that complex machine, and its characteristic polynomial is the diagnostic barcode. This polynomial captures the core identity of the matrix, such as its eigenvalues, which describe how it stretches or shrinks space. The Cayley-Hamilton theorem states something incredibly magical. If you feed the machine its own diagnostic barcode, the machine perfectly neutralizes itself and powers down to zero. Now that we understand the conceptual idea, let us look at the formal mathematics. The characteristic polynomial is found conceptually by taking the determinant of the matrix A minus lambda times the identity matrix I. Here, lambda is a scalar variable representing eigenvalues, and I is the standard identity matrix. When you calculate this determinant, you get a standard algebraic polynomial. The Cayley-Hamilton theorem states that if you replace the scalar variable lambda with the matrix A itself, the entire polynomial evaluates to the zero matrix. Notice that the constant term C0 gets multiplied by the identity matrix because we are now operating entirely in the world of matrices. This formula we just saw can be visualized very simply. Look at the diagram on screen. We start with our original matrix A on the left side. We feed it directly into its own characteristic polynomial, which acts as a mathematical function or machine. The output on the right side is a completely empty zero matrix, where every single entry has become zero. This visual perfectly captures what we mean when we say the matrix satisfies its own fundamental equation, leaving absolutely nothing behind. Before we prove why this works, let us see this with a concrete example. We are given a simple 2x2 matrix A, and we want to verify that the theorem holds true. First, we need to find its characteristic polynomial. We subtract the scalar variable lambda from the main diagonal entries. Then, we calculate the determinant of this modified matrix by multiplying the main diagonal elements and subtracting the product of the off-diagonal elements. Expanding these algebraic terms gives us the raw expression for our polynomial, which we will simplify next. Continuing with our calculation, we simplify the algebra to get our final characteristic polynomial, lambda squared minus 5 lambda minus 2. According to the theorem, replacing the scalar lambda with the matrix A should result in 0. Remember, the constant 2 becomes 2 times the identity matrix I. To verify this matrix equation, we first need to calculate A squared. We do this by multiplying the matrix A by itself using standard row by column matrix multiplication rules, which gives us a new matrix with larger values. Now we gather all our pieces to finish the verification. We calculate 5 times A by multiplying every entry in our original matrix by the scalar 5. We also have our identity matrix scaled by 2. We substitute these calculated matrices into our mean equation and perform the subtraction element by element. For instance, the top left entry is 7 minus 5 minus 2, which leaves exactly 0. As we do this for every position, every single entry perfectly cancels out. The physical meaning here is that the matrix perfectly neutralizes itself, proving the theorem holds. Now that we have successfully used the theorem, let us understand why it works for every square matrix. We start our proof by setting up the definition of the characteristic polynomial, using the scalar variable t. In linear algebra, there is a fundamental property that any matrix multiplied by its adjugate equals its determinant multiplied by the identity matrix. We apply this universal mathematical reasoning to the specific matrix expression T times I minus A. Since the determinant part is exactly our polynomial P of t, we substitute it in. This creates a powerful bridge linking our matrix directly to its defining polynomial, setting the stage for the rest of the derivation. Moving forward with our derivation, we must recognize that the adjugate matrix itself contains polynomials. Because of how determinants work, we can write this entire adjugate as a polynomial in T, but with unknown matrix coefficients, which we will call B. We also write out our characteristic polynomial explicitly with its scalar coefficients C. We take both of these fully expanded forms and substitute them back into our bridging equation. The mathematical reasoning here is to compare the two sides. The left side is now a multiplication of two matrix polynomials, and the right side is our scalar polynomial multiplied by the identity matrix. This connects directly to our next step of matching terms. To make sense of this massive equation, we imagine expanding the left side and matching the coefficients of identical powers of t from both sides. The constant terms give us our first equation. The terms multiplied by t give us the second. And this logical pattern continues all the way up to the highest power. Now comes the brilliant mathematical intuition behind this proof. Because we ultimately want to evaluate the polynomial at A, we need to create powers of the matrix A. We do this by multiplying each of these matched equations by increasing powers of A, starting from the identity matrix up to A to the power of n. Finally, we take all these newly multiplied equations and add them vertically together to see the final result. Look closely at the mathematical reasoning on the left side. The negative A times B0 perfectly cancels with the positive A times B0 from the next line. This cascading cancellation is called a telescoping sum, and it is the intuition behind why the whole system collapses. The entire left side becomes the zero matrix. Meanwhile, the right side simply adds up to exactly the definition of our characteristic polynomial with A plugged into it. This gives us our final derived expression, proving the theorem is universally true. So, we have proven that the theorem holds universally. This brings us to an important question. Why does this abstract math matter in the real world? The Cayley-Hamilton Theorem is a massive time saver and a foundational tool in advanced engineering and physics. It is heavily used in control theory, which is the science of making complex systems like self-driving cars behave correctly. When engineers need to calculate extremely high powers of a matrix to predict long-term behavior, this theorem allows them to rewrite those high powers as simple short combinations of lower powers. It also provides a brilliant algebraic shortcut for finding matrix inverses. Let us see how this inverse shortcut works using our previous matrix. Finding an inverse using traditional row reduction can be a tedious and error-prone process. Instead, we start with the characteristic equation we already verified for matrix A. Our primary goal here is to get the identity matrix completely isolated by itself on one side. We move the 2i term to the right side and then divide both sides by the scalar number 2. By treating the matrices almost like regular algebraic variables, we easily rearrange the formula, explaining why this algebraic approach is so much faster. Now that we have an isolated expression for the identity matrix, we factor out an A from the right side. By fundamental definition, any matrix multiplied by its inverse will always equal the identity matrix. Because A multiplied by the expression inside the parentheses equals I, that expression must logically be the inverse of A. We have derived a beautiful, simple formula for the inverse without doing any complex row operations. We simply substitute our original matrix A and the scaled identity matrix into this new formula to prepare for the final arithmetic. For the final steps of our calculation, we follow the standard order of operations and perform the matrix subtraction inside the parentheses first. This step adjusts the values on the main diagonal while leaving the other numbers alone. Finally, we handle the scalar multiplication on the outside by multiplying every single entry inside the new matrix by 1/2. This scales the numbers down to their final correct values. The physical meaning of this final answer is that we have successfully found the exact inverse matrix using a completely alternative, highly efficient algebraic method. We have covered a lot of ground today, so let us review the most important ideas. The Cayley-Hamilton theorem is a profound result, stating that every square matrix satisfies its own characteristic polynomial. By simply replacing the scalar variable with the matrix itself, the entire expression evaluates to the zero matrix. This powerful property bridges abstract algebra and practical computation, allowing us to easily calculate inverses and manage high powers of matrices. You have tackled a very advanced topic today. Great job following along.